So this is another short chapter with a brief introduction to carbon CO2 extraction from the atmosphere. For summary, let's look at this nice figure again from this paper here in Nature. This is showing atmospheric CO2. This keeps changing, but nonetheless, let's look at relative amounts. 3,150 gigatons of CO2. Net atmospheric growth is 17 gigatons CO2 per year. And so there are fluxes and stocks, as we would say, or reservoirs and fluxes. Energy is putting out 13 gigatons CO2. Buildings, industry, transport, which is always a big item, a big ticket item. Agriculture, as we said, amounts to about 25%. Land use change, and then there are land sinks taking up 12 gigatons and ocean sink taking up about 9 gigatons, with stocks in fossil fuels ranging in estimates, but reserves and resources here massive numbers. So it's not like you can dig it all up and burn it, because that CO2 is going to stay in the atmosphere unless our CO2 sequestration and extraction becomes so good that we can happily burn carbon fuels. Lithosphere has huge amounts of CO2 as well, and of course there is stocks in vegetation, in the biosphere in general, in the soils, in the hydrosphere, seawater, and sediments. Okay, so there are various pathways shown here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are chemicals. Even on the inside, I get this chopper going by. So making chemicals from CO2 from the industrial emissions, fuels from CO2, products from microalgae, concrete building materials, which is down here. Sorry, where is 4, 4, 4, 4, 4, 3, 4 here? CO2, EOR. What is okay? Emissions. God damn it! What is EOR? What is CO2 EOR? Let me just Google it while I'm doing this. Sorry, I should have looked it up. CO2 EOR is enhanced oil recovery. I should have known that. So pumping CO2 into oil wells to push out more oil that is stuck and not easily accessible by the pumps. Bioenergy with carbon capture and storage, BECCS, enhanced weathering, which we didn't talk about much, but I don't know what I did with my biochar. I have a biochar, yes. Enhanced weathering is basically, let's say, grinding up rocks like the ultramafic rocks, which are also called ultra basic rocks, because adding carbonic acid accelerates their weathering and converts CO2 locked up as calcium carbonate, for example, into HCO3 minus or bicarbonate, which can flow through the rivers into the ocean and remain stable and be used up and exported to the sediments, which have this huge reservoir as well. But there are lots of logistical and cost issues in terms of grinding the rocks, producing aerosols and other material there, transporting it, where to spread it, and how to maintain the cycle, etc. So it sounds good, theoretically has high potential, but long way to go. Forestry techniques, soil carbon sequestration techniques, and then biochar. Right? So biochar is basically when you have a cycle with photosynthesis and decomposition and returning as CO2. What you can do is take the biomass produced by photosynthesis and use what is called pyrolysis, a high temperature process where 50% of the carbon is converted to carbon that can be, it's solid carbon. It's not like coal. It's much more pure carbon, and other 50% can go into the synthesis gas, the intermediate product that we talked about, or bio oil, for example, as energy production, and then 50% less actually returns as atmospheric CO2. So you are modifying this cycle to reduce emissions and accumulation in the atmosphere. And this biochar is very rich in carbon and is used in agricultural lands, and there are other applications that I'm not going to go into. But this information here is from the agricultural consultative agricultural group or some such thing, is showing by region in 27 the biochar market share. In North America it's about 61%, almost all of it. In Europe, Asia, Latin America, and Middle East and Africa, there is a smaller percentage of the biochar market. In India, there are some non-profits and NGOs and startups doing biochar as well. So converting agricultural residues and so on to biochar and putting it back on the fields to enhance the carbon content of the soils is a really good idea, and if it remains carbon neutral or additional carbon can be put into the soil, then that's a very promising way to also have co-benefits of higher production with high organic soil content, soil organic carbon content. Okay, so this is showing again what to do with storage. So CO2 in the atmosphere, either direct air capture or land-based capture. So there is emission in use happening here. There is emission in transformation, or it can be converted into carbon product, and they can go into industrial capture to produce concentrated CO2, which can be stored in the lithosphere or in the hydrosphere, and it can be extracted to produce carbon products on demand, and you can also put additional carbon in the biosphere. So this is enhanced oil recovery pathway here, and here these blue arrows, these are fuel pathways, so air capture and transformation into carbon product, and these are forestry pathways here into the biosphere, which obviously releases back into the atmosphere on some time scales. Okay, so enhancing soil carbon obviously goes in there, but we have talked about the caveats of each of these things. So just to look at the scenarios where you can look at the break-even costs in 2015 US dollars per ton of CO2 utilized in this manner. Where there are numbers, negative numbers, it means they are already profitable and don't need additional incentives. But there are obviously lots which are positive, which means they have a break-even cost of like $1,000 per ton of CO2 used for cement production. This is the Fischer-Tropsch fuels, the process that we talked about: methane, microalgae, methanol, BECCS, aggregates, and various other options here, like biochar, enhanced oil recovery, methanol, BECCS here, and so on. Okay, so this is the low scenario where you have the potential and the in terms of gigaton CO2 utilized by 2050. This is the low estimates based on the scenario assumptions, and these are the high estimates. So you can see that this range is getting into the 20 gigaton that we would need to bend the curve towards 2 degrees centigrade global warming target. But again, these are estimates, and these are estimated in terms of, let's say, 2015 US dollar per ton. But as we said, the investment always has to be looked at the present discounted value. So all sorts of complicated assumptions and uncertainties are involved in here. And I won't go into these details, but you also have to worry about the duration of the storage in terms of whether they are days, months, decades, or centuries. So some are centuries, like aggregates, forestries are decades, methanol is days or months, and so on. Okay, so how long you can store it, how much you can store, how long it's going to stay there, and what is the break-even cost, and eventually how we are going to pay for all that. Carbon tax, maybe, that's what we talked about before, but these are all the challenges.